our last example here together. I saved the best for last, and this is my favorite one of the three. Part C, let's look at the common interior of r equals 2 cos 3 theta and r equals 1. Well, you might recognize that first function as the Rose curve we did in part A. And you may remember that something that looks like r equals 1, that's just a circle with radius 1. So graph these in Desmos, of course, and you will find this. I'll show you what this is all about. That'll make sense in a moment. Here's what the graph will be, right? We've got that 3-petaled rose curve that gets traced out this way when you go around a period of pi. This on the outer edge is 2, and then we've got that circle of radius 1, so that should be about right at halfway, half of that first rose curve. Okay, so the common interior would be the parts between both of them. So we're going to be inside the rose curve, but then also kept inside the circle. So we'll have this little bit there, but then we'll also have this part there, this part here. Okay, so sort of like a pinwheel, like a propeller on an airplane is what that looks like to me. But obviously we're just finding those areas. Common interior, always fun. Okay, definitely take advantage of symmetry here. I mean, we can really do something cool. Obviously we just want to focus on one petal, but then even let's just do the upper half of even that one petal. So we'll get the area of this darker shaded region there, and then how many of those appear, when we're done? Well, we'll have 6, right? 1, 2, this will have 2 more, so there'll be 6 of these little areas. And that little shaded region I've like zoomed in for this drawing over here on the other side. So we know that's passing through at 1, this is out at 2. I've only drawn the top half of that part of the rose curve, and then the circle, right, this would be at 1 as well with radius 1, like that. Okay, so I would advise in Desmos, zoom in like in this first quadrant. Here's what we're looking for. There's 2 angles that we need. So there's an angle that cuts off the rose curve, right, where the rose curve goes back to the pole. In fact, we already know that back from part A. This was pi over 6, right, and that might be clear just in Desmos as well. And it would be easy to confirm, if we plug it into the rose curve, we do get 0. It draws back right there. There's another angle that we need, where they intersect. Okay, so this is kind of tough to draw without a straight edge, but I'm going to try it. So right there, we're going to go through, and it's hard to distinguish my lines kind of overlaying on one another. We need to find where that occurs. Now, I don't know, I forget exactly, I don't have Desmos up right now myself. I don't think they divide these up, into every possible little increment, that might occur. So, they'll do like, the more typical things like pi over 6, pi over 3. I think they even do like pi over 12. But this one is not going to be any of those. Okay, where it crosses through right there. So where does that happen? Well, how can we find out? We could set these equal, right? That's where they would cross. I don't think I actually have that in my notes. No, I don't. Okay, so we'll just do it right here. So where's the intersection? well, that's where these equal 2 cos 3 pi equals 1. So we'll solve for theta. That's when cosine 3 theta equals a half. Now what's convenient is we're just looking for the answer in quadrant 1. So our calculator will generate the result for us. Although, let's see what would happen. So if we take an arc cos of both sides, full arc. Oh, pi over 3. Okay. So your calculator might be able to produce, let me show you what I did. So I did arc cos 0.5, and it gave me this decimal, but then I used my little double arrow feature right there, that button, and it realized that that was pi over 3. Let's see, what would happen if I did it as a fraction? No, it doesn't like that either. So somehow, we're smarter than calculators, obviously. The cosine of what angle would give you a half? Well, if you realize the cosine of pi over 3 would give you a half, then you're good. So we know that the 3 theta equals pi over 3. Well, what does that make theta equal? Pi over 9. Okay, so this occurs at pi over 9. Again, Desmos, I don't think they show pi over 9. I think they only divide it into twelfths. So we need a little algebra there, a little solving with trig to get that one for us. Okay, why is it that we need, like, how are these integrals going to work? So it turns out there's 2 areas. The first area goes from 0 to pi over 9. 0 to pi over 9 is bounded by the circle. It's the area inside the circle from 0 to pi over 9. It's that wedge. Then we'll take a second integral from pi over 9 to pi over 6. And it's so difficult to see, but it's this tiny little sliver that goes, that like little bubble that goes beyond and then ends up coming back down to the pole. So this tiny little bit that's above that line at pi over 9. And I've got these noted here. Let's consider area 1, bounded by the circle from 0 to pi over 9. And area 2 is just above that. It's bound by the rose curve from pi over 9 to pi over 6. This is the most difficult part of the problem. So if this sort of thing is unclear to you, come to the live session. Read further in the textbook. Look at other resources. This is everything right here. Obviously, we'll execute the integral. That's important, but the setup, obviously. Okay, so we've got our 2 areas. And I'm going to present them like side by side, like so, just the way I have it on the page. So area 1, it's the circle, so r equals 1. So we've got 1/2 0 to pi over 9, 1 squared d theta. Area 2 is bound by the rows. So I've got 2 cos 3 theta in there, 1/2 integral pi over 9 to pi over 6. 2 cos 3 theta, quantity squared d theta. So we'll take both of these, obviously we'll add them. Okay, so kind of getting the side-by-side action. Maybe let's just walk through this one. Well, the 1, all right, that works out pretty good. So that antiderivative is just theta, and because it's from 0 to pi over 9, plugging in gives us pi over 18. Now if we go back to this one, well, we already did this antiderivative earlier, so it's going to be the same thing. If we square, well, the 2 becomes a 4, pull the 4 out, multiply by the half. and we get the cosquared. Okay, here I would use the trig identity. So what, 1 plus cosine 6 theta all over 2. Well, I didn't write that just because it was a repeat, but the divided by 2 would come out, cancel with that 2, and the 1 plus cosine 6 theta antiderivative is theta plus 1/6 sine 6 theta. So it might be helpful to have that other line written in the middle. And if I was working this on the board in the room, I probably would write that again. Then we're going to integrate pi over 9 to pi over 6. So let's plug those in. Plugging in pi over 6 isn't too bad. Pi over 6, and then there we get the sine pi, so the 0. Subtract pi over 9. Plugging pi over 9 in for theta here would give us the sine of 2 pi over 3, which ends up being root 3 over 2, but then we multiply by the 1/6, root 3 over 12. Okay, put these together and you'll have, well, it turns out you have pi over 18 again, which is interesting. Pi over 18 minus root 3 over 12. And then put those all together. So we'll add a1 plus a2. And at the same time, we recognize we need 6 of those for all the area we are asked about. So adding those, multiplying by 6, 2 pi over 3 minus root 3 over 2 is the common interior of that rose curve and that circle. All right. To end this video and this section, I'm going to show you guys polar arc length, the formulas for those. I actually don't have any examples for these. They really are not emphasized a ton. There's not a whole lot of homework on it. So I'm just going to let you guys go for it there in the homework. Here's the formula. Integral from alpha to beta, big square root r squared plus r prime squared d theta. And that looks really familiar to the parametric equations, the parametric style of arc length. Here it is again. I believe this is the way the book presents it. Instead of r's, they have f of theta, and r prime, it's f prime theta. So that style, you know, is maybe easier to remember. I don't know. I kind of like the r's. Why is this? Why is this the formula? So I'm not going to go into all the details, but just to give you an idea of the proof without everything. So remember, the parametric arc length looked very similar, but it was dx over dt squared plus dy over dt squared inside that big square root. Well, if we're using polar, we can go about it the same way. Just instead of t, we have theta. Dx over d theta squared plus dy over d theta squared. There's a really close connection between parametric and polar. Why is that? Well, remember this. In parametric, we have two different functions for x and y, right, in terms of our parameter. Well, that really is the case in polar as well, right? We could say x equals r cos theta and y equals r sine theta. That's how we connect x and y with r and theta. So in a sense, polar is like a parametric representation, you know, with these two things the case. Now, what is the r? Well, the r is what the function is, right? That's f of theta. So you would just put that whole thing in place of the r. So what happens is, if you think of x and y as defined this way, and you use that same style, if you take these derivatives in terms of theta, you know, maybe using this, and then square them and add them together, it ends up being exactly this style, and then it ends up plugging it in there. It ends up simplifying, and it'd probably be easiest to see with the f of theta, f prime theta, ends up simplifying exactly to that. The sine squareds and cosine squareds end up going away completely when you work through all that algebra. Okay, so without all those details, there's your polar arc length formula. Check out the homework. See you in the live meeting.